The third part of this chapter is forces and acceleration. Here we're going to use Newton's second law that states that resultant force must be equal to mass times acceleration. And we've shortened this to F equals ma. Now, if an object is falling freely under gravity, so falling down to the ground, it will accelerate at a rate of what's said to be about 9.8 meters per second. So if something is dropped from rest, after 1 second its speed is 9.8 meters a second, after 2 seconds 19.6 meters every second, after 3 seconds it will travel at a rate of 29.4 meters per second. And as I said in an earlier lesson, weight is equal to mass times gravity. We take G to be 9.8. Now you need to be careful with your calculations here because we're taking G to two significant figures. So any answer you give that involves G in the calculation should only ever be given to two significant figures. If you give it to any great degree of accuracy, you're on dodgy ground because you're using information to a less degree of accuracy. So let's just get example 5. It says that find the acceleration of a particle of mass 1.5 kilograms acting on a resultant force of 6 newtons. So we're using standard index there, kilograms and newtons. If you're given a question involving grams, you need to convert it first to kilograms. So using Newton's second law, F equals ma, the resultant force equals 6, which is equal to 1.5 times the acceleration. Therefore, if we bring that over as divide, acceleration must be 4 meters per second. Example 6. We're given a force diagram here. So we've got a block, 2 kilograms. We've got a weight acting down of 2g, force upwards of y, force across of x, force to the left of 4. Now it's normally fine to leave g in your answers, however we'll work 2g out as 19.6, 2 lots of 9.8. It's worth learning some of the multiples of 9.8 because it'll help you be a bit quicker in your calculations. Now it says in each of these diagrams the body is accelerating as shown. I haven't put that in, so it's accelerating towards the right at a rate of 2 meters per second. Now what that also means is vertically it must be in equilibrium because there's no vertical acceleration. So that means straight away I can say that y must be equal to 19.6 newtons. These two forces must be balanced. It's accelerating to the right, which means there must be a resultant force to the right, which means x must be bigger than 4. If x were to be equal to 4, it will be at rest, we know, or move at constant speed. If x were to be less than 4, we would accelerate to the left. So because we know it accelerates to the right, we know x must be bigger than 4. So using Rf equals ma, that means all the forces in the direction of the acceleration to the right minus all the forces in the opposing direction must be equal to m times a. That gives us x to the right minus 4 to the left must be equal to m, which is 2, times acceleration, which is also 2. So x minus 4 equals 4, meaning that x must be equal to 8 newtons. In part B, got a block, 4 kilograms, weight acting downwards of 4g, which is 39.2 newtons. A force going upwards y And we've also got here, rather annoying, a force downwards here of 20. Now I don't like that. I'd never have that in my force diagrams. I would also have force going into the block down here. So I've got another 20 here, making it 59.2. Force to the right, x. Force to the left, 80. This time though, it's accelerating to the left at a rate of 2 meters per second again. Now again, there's no vertical acceleration, so the resultant force vertically is 0. It's an equilibrium, which means all the forces up must equal all the forces down, so y equals 59.2 newtons. Horizontally, x must be less than 80. It must be less than 80 because it's accelerating to the left, meaning there must be a resultant force to the left. Now I could do resultant force, as I've done here, to the right, but you might as well go with the directional acceleration to make the calculations easier. So resultant force to the left is all the forces to the left minus all the forces to the right equals m times a, where the acceleration is also to the left. So I've got 80 take away x equals 4 times 2. 80 take away x equals 8. Therefore x must be 72 newtons. Okay, those are about all the examples. Oh no, there's one more example, example 7. So example 7. It says that a body of mass 5 kilograms is pulled on a rough horizontal table. Rough meaning there's going to be friction. It's pulled by a force of magnitude 20. So I'm going to have a frictional force pulling it back. And it says that frictional force is of magnitude 4 newtons. Okay, we would also have the weight of the force, which would be 5g, and normal reaction, which must, because there's no vertical acceleration, would also be equal to 5g. I don't think the question involves that though. It asks us firstly for the acceleration of the body. Now, as I said before, friction is a variable force. It ranges from 0 to what's called F max. Now, if F max was to say 25, so the most friction could ever be is 25 in this direction, but it's only been pulled across a force of 20, then the friction will be 20. Because if it were to exceed that and be the maximum friction force 25, it would start accelerating in that direction, which is really weird. If you're pulling it that way and it starts accelerating the opposite direction, something scary is going on. In this case, the frictional force is 4, so it's already its maximum. The maximum it could possibly be is 4. So overall, we've got a resultant force of 16 to the right. So it's going to accelerate to the right. So resultant force to the right, because that's like the bigger force. Forces to the right minus forces to the left equals ma. So I've got 20 take away 4 equals 5 times a. And this is where the 16 comes from. Therefore, I equals 3.2 meters per second per second. It then wants the distance travelled by the body in the first 4 seconds, and we're told that the body is initially at rest. So here we're going to need to do a bit of suva. So initially at rest, it wants the distance travelled in the first 4 seconds, and we've already worked out the acceleration is 3.2. So it wants distance travelled. So we need the formula that hooks up S, U, A and T, and you need to memorise these. S equals ut plus half at squared. So the distance travelled is ut, which is 0, 4 times 0. So it's just going to be half a, 1.6 times t squared, 4 squared. 1.6 times 16, it's going to be 25.6, I think. Yeah, 25.6 meters. The magnitude of normal reaction I've already done is 5G, which is 49 newtons. Okay, that's all the examples there before exercise 10C. So now crack on with that.